Doug Johnson is a maintenance training specialist. From years of experience, he knows how important pumps are in all areas of industry. When he teaches pump maintenance mechanics, he uses this experience to stress good pump maintenance procedures. Keeping pumps in good condition and heading off serious problems before they occur. That's what pump maintenance is all about. And it starts with you learning everything you need to know to do the job properly. To begin this unit on centrifugal pumps, let's take a look at pumps in general. There are two types of pumps: centrifugal pumps like this one, and positive displacement pumps, such as this rotary type. These two pumps don't just look different, they work differently too. But as we'll see, they both have the same purpose: to move fluids from one place to another. When we say fluid, we mean any substance that can be pumped, from water to oil to refrigerants to liquid chemicals, even air. In the pumps we'll talk about, water is the fluid being moved. The real difference between centrifugal pumps and positive displacement pumps, then, is not what they do, they both move fluids, but the way they do it. To understand how each type operates, let's first look inside a piston-type positive displacement pump. As you can see, a piston-type pump is made up basically of a piston rod, which is connected to a motor or other prime mover, a cylinder, and two valves, all inside a casing. On the first stroke, the piston moves back, creating a suction in one end of the cylinder. This suction opens the suction valve and draws water into the cylinder. On the return stroke, the piston moves forward, putting pressure on the water. The suction valve closes, the discharge valve opens, and the piston pushes or positively displaces the water out through the discharge piping. Okay, now, let's compare this pumping action to that of a centrifugal pump. As we look inside a centrifugal pump, notice that there is no piston and no cylinder. Instead, there is a circular device with a series of curved vanes extending outward from its center. This is the impeller. It's attached to the pump shaft so that when the shaft rotates, the impeller rotates with it. Unlike a positive displacement pump, which fills and empties as the piston moves, a centrifugal pump must be full of water, or prime, at all times during operation. Water from the suction piping enters the impeller through the suction eye at the center. It flows outward to the edge of the impeller through a widened chamber called a volute, and out of the pump through the discharge piping. The force that moves the water along this path is created when the pump is turned on. As the shaft and impeller rotate, the vanes of the impeller stir the water, causing it to move in the same direction. This rapid circular motion creates what is called a centrifugal force, and it's this force that gives centrifugal pumps their name. To demonstrate how these pumps work, let's see if I can create a centrifugal force in this bowl of water. I'll use this stirrer attached to an air drill. Now, imagine that the bowl is the casing of a centrifugal pump. Like the casing, it's filled with water. This stirrer will act as the impeller. Now watch what happens when I turn the drill on. As the water begins to move in a circle, a centrifugal force is created. This force pushes the water away from the blade out toward the edges of the bowl. The faster the water moves, the harder it's pushed outward. Of course, if there's nothing to keep it in, it spills over the edges of the bowl. In a real centrifugal pump, of course, the casing keeps it from spilling out over the edges. Anytime you have an object or a fluid moving in a circle, a centrifugal force is created that pushes that object or fluid away from the blade to the outer limits of the circle. By the way, if you try this experiment, don't use an electric drill, or the results will be shocking. In a centrifugal pump, as the impeller spins and centrifugal force throws the water outward against the casing, two things happen. First, as the water moves outward, it creates a suction at the eye that draws more water into the impeller. This provides a constant flow of fluid into the pump. Second, the outside edge of the impeller rotates through a greater distance than the inside edge. This means that as the water moves outward, it must gain speed to keep up with the rotation of the impeller. When it finally reaches the volute, the water is flowing very fast and contains a large amount of energy. As you can see, the volute widens gradually until it connects to the discharge piping. As the water flows into the volute then, it must spread out to fill this increased area. This expansion causes the water to slow down, and its speed is converted into pressure. It then has enough force to move through the discharge piping. This is a very basic explanation of the way centrifugal pumps work. There are several parts of centrifugal pumps that we haven't even mentioned yet. But before we go into detail, use your text to review the types of pumps we've talked about and the way each type works. So far, we've identified the major parts of a centrifugal pump and seen how they move fluids. In this segment, we're going to take a closer look at centrifugal pumps. Now, just to make things easier, we brought this pump into the shop because there's plenty of room to work here. But you may have to work on pumps like this, connected to a motor and to suction and discharge piping. This is the inboard or motor end of the pump. This end of the shaft is connected to a motor or other prime mover. The suction piping that brings water into the pump connects to this flange here. And notice that the suction port is larger than the discharge port here on the other side. Knowing that the discharge opening is often smaller than the suction opening will help you to distinguish between them. This is the gland sealing line. It's part of the pump's sealing and lubrication system, which we'll talk about later. The casing holds the water inside the pump. As you can see, this one opens horizontally. We've removed the casing bolts so that the upper casing can easily be lifted off to expose the internal parts. Here, of course, is the impeller. Along the edge, you can see the tips of the vanes that get the water moving as the impeller spins. In the center, where the impeller attaches to the shaft, is the suction eye, where the water flows in from the suction piping. There's a suction eye on each side. Also, on either side of the impeller are casing wearing rings. These rings do a very important job. They keep water that's slung out of the impeller from leaking back into the suction eye. Why is this important? Well, as you can see in this cutaway drawing, there's a gap between the impeller and the casing. This gap gives the impeller room to rotate. If the space were not there, the impeller would constantly rub against the casing and wear itself down. However, if there's too much of a gap, water circulates from the discharge back to the suction eye instead of leaving the pump. To prevent this, casing wearing rings fit snugly between the impeller and the casing, closing off most of the gap and reducing the amount of leakage. Although these rings do wear, they can be pretty easily replaced. Going outward from the impeller and the casing rings, we next find the packing gland. The packing gland includes the throat bushing, several rings of packing material, the lantern ring, some more packing material, and the gland follower. Together, these parts reduce the amount of water that leaks out along the shaft. They also prevent air from leaking into the pump. The packing gland fits into a space called the stuffing box, where the shaft passes through the casing. One end of the stuffing box is closed off by the throat bushing. The throat bushing keeps the packing gland from being pushed into the suction of the impeller. Right behind the throat bushing are the first rings of packing. Packing is made of a soft, pliable material. When properly fitted into the gland, the rings fill the space between the shaft and the casing. Because packing material is soft, the shaft can rub against it without being damaged. But no matter how soft the packing is, it has to be kept lubricated. Otherwise, friction caused by the rotation of the shaft would generate enough heat to scorch the packing and cut grooves in the shaft itself. Usually, packing is coated with its own lubricant, either graphite or Teflon. Still, this isn't enough. More lubrication is needed to keep friction at a minimum. In a pump like this one that moves water, we can simply use some of the discharge water for lubrication. This water is delivered from the discharge through the gland sealing line to the lantern ring. From the lantern ring, it leaks through the stuffing box and out the end of the gland. Remember, though, that some pumps move chemicals, and it might be dangerous to let these chemicals leak out. In such cases, we have to worry not only about lubrication, but also containment. One solution is to have water brought into the packing gland from an external source. This water is delivered through the gland sealing line and forced into the channel in the lantern ring, just as it would be in water pumps. Now, as you can see on this lantern ring from a similar pump, there are holes on either side of the channel. These holes allow water to escape from the channel. Some water flows inward, blocking the chemicals from leaking out, and the rest flows outward along the shaft, cooling and lubricating the packing before leaking out at the end of the gland. The final part of the packing gland is the gland follower. Normally, this one would be held in place by the same bolts that hold the casing. The gland follower holds the packing and the lantern ring firmly in place against the throat bushing. By tightening or loosening these nuts, the gland follower can be adjusted to exert the right amount of pressure on the packing. This pressure controls the amount of sealing water that flows through the gland. That covers the sealing and lubrication system. Now, at both ends of this pump are shaft bearings. Two bearings are located here inside this housing. One bearing, the thrust bearing, keeps the shaft from moving back and forth this way. The second bearing, the radial bearing, keeps the shaft from moving radially, that is, up and down, or back and forth. A third bearing, another radial bearing, is located on this end of the pump. Two things we haven't looked at are the shaft itself and the volute. The shaft in this centrifugal pump looks like this. One carefully machined piece that fits the pump perfectly. As we'll see, though, shafts can be damaged in a lot of ways. So, some pump shafts have separate sleeves that fit over them, cheaper to replace than shafts are. Another part you should know about is the volute. The volute is the part of the casing where fluids spread out, slow down, and gain the pressure they need to travel through the piping. On pumps like this, you can't see the entire volute, but you can see some of it. This is where the volute begins, goes around, widens, and extends underneath the impeller in this pump and ends here on the other side where it connects to the discharge pipe. Now that you've seen the parts of this pump, you should know that all centrifugal pumps have the same basic components. Only the size and arrangement of the parts will vary from pump to pump. We'll see a few different types of centrifugal pumps after a short break. Following the right maintenance program starts with knowing what type of pump you're working on. There are 4 basic ways to categorize centrifugal pumps. The first is based on the position of the shaft during pump operation. The second depends on how the impeller is designed. The third is determined by the number of impellers used. And the fourth depends on the design of the volute. In the first category, pumps are described by the position of the shaft, either horizontal or vertical. In horizontal pumps, the motor and pump are on the same level, and the pump shaft runs parallel to the ground. In vertical types, the motor is located above the pump, and the shaft is perpendicular to the ground. Vertical pumps take up less floor space than horizontal pumps do, and they are used where fluids must be pumped out of tanks or reservoirs below floor level. In the second category, there are several different types of impeller design. This is a closed impeller. It gets its name from the fact that the vanes are enclosed between 2 metal faces called shrouds. High-pressure centrifugal pumps that move clear, non-clogging liquids, such as water, usually have closed impellers. This is an open impeller. Notice that there's no shroud at all. Open impellers are used on low-pressure units to pump slurries and other thick fluids that might clog a closed impeller. A semi-open impeller is sort of halfway between an open and a closed impeller. As you can see, it does have 1 shroud, and the vanes are not completely enclosed. Semi-open impellers are also used in moving thick fluids that could clog a closed impeller. Another difference among impellers is the way their suction port is designed. Some, like this one, have only 1 suction eye. They're called single suction impellers. This closed impeller is a double suction type. It has 2 suction eyes, 1 on either side. The advantage of a double suction impeller is that incoming water exerts an equal pressure on both sides of it. In the first 2 categories, then, a pump can be horizontal or vertical, with a closed impeller, open impeller, or semi-open impeller, and either single or double suction. Now, the third category involves the number of impellers used in a pump. So far, we've talked about pumps having only 1 impeller. These are called single-stage pumps. They're okay for low-pressure jobs. But when you need high discharge pressure, you either have to get 1 large impeller to spin a lot faster, which in most cases isn't practical, or you can use a pump with more than 1 impeller. This is a multi-stage pump. It has 3 impellers, or stages. Let's look inside so we can see how this pump works. Multi-stage pumps work like a number of pumps connected in sequence. Water enters the suction eye of the first impeller, spins around and out, gaining speed the whole time. When it reaches the first stage volute, its speed is changed into pressure. The pressurized water is then discharged into the suction eye of the second impeller. This second stage adds more energy in the form of speed. Then, in the second stage volute, this added energy is converted into more pressure. Finally, the water discharges into a third stage, which increases the pressure even more. The end result is that the pressure has been increased through 3 stages instead of only 1. That covers the categories for impeller design and the number of impellers used. As we've seen in the first 2 categories, a pump can be classified as horizontal or vertical, and as an open, closed, or semi-open impeller type, with either a single or double suction. In the third category, pumps can be either single or multi-stage. The fourth category involves the design of the volute. In this pump, the volute is formed by the casing itself. Basically, the volute is a chamber that allows the fluid to spread out, slow down, and gain pressure before leaving the pump. Any pump where the volute is formed by the casing is called a volute pump. This is another type of pump called a diffuser pump. Notice that it doesn't seem to have any volute at all. What it does have is a series of stationary diffuser vanes surrounding the impeller. Diffuser vanes accomplish the same thing a volute does. Water leaving the impeller travels outward between the vanes, which spread out and slow the water, giving it pressure. Now that you've seen how pumps are classified, you should be able to figure out what type of pump this is. First, look at whether the shaft runs horizontally or vertically. In this pump, the shaft is horizontal. Next, look at the impeller. Since this impeller is shrouded on both sides, it's a closed impeller. Also, there's an eye on each side, making it a double suction type. The number of stages is easy, 1. And by looking at the shape of the pump, you can see that the casing forms a volute, making this a volute pump. A lot of times, the type of impeller in a pump is not mentioned. So what we have here is a horizontal, double suction, single stage volute pump. In the centrifugal pumps we've seen so far, water moves at right angles to the shaft. For this reason, they're also called radial flow pumps. But there is another type that's classified with centrifugal pumps, the axial flow pump. Axial flow pumps, like this propeller type, get their name from the fact that water flows through them parallel to the axis of the shaft. To see how a propeller-type axial flow pump operates, let's start with its parts. The suction bell, the impeller, which is shaped like a propeller and gives the pump its name, the bearing, diffuser vanes, the packing gland, the shaft, and of course, the casing. Fluid enters through the suction bell and travels to the impeller. Since the impeller is shaped like a fan blade, it moves fluid in the same direction that a fan moves air, in a straight line parallel to the shaft. The fluid leaves the impeller and enters the diffuser vanes, which break up the turbulence in the water and help smooth out the discharge. Propeller pumps are useful where a lot of water has to be pumped at fairly low pressure. The reason I mention axial flow centrifugal pumps is that they have the same basic maintenance problems that radial flow pumps do. Keep this in mind when we discuss common pump maintenance problems in the next segment following this short break. When it comes to maintenance, pumps are no different from other types of equipment. Sufficient lubrication is absolutely necessary, and pump and motor shafts have to be properly aligned. And of course, you have to keep an eye out for signs of wear or damage. Some problems, like excessive leak-off, are easy to spot. Others can only be detected by an experienced eye or a trained sense of hearing and touch. As you gain experience in pump maintenance, you'll learn to read a pump almost at a glance. You'll learn what a pump should sound like and how much vibration is normal. Once you know how a pump is supposed to act, detecting problems will be a lot easier. There's really nothing you can substitute for experience, but there are maintenance guidelines and procedures to follow. And that's what we'll be looking at in this segment. In most cases, you'll find out that there's some problem with a particular pump when the pump operator submits a work request to the maintenance foreman. But the work request usually won't tell you exactly what the problem is. The first step in this situation is for you or the maintenance foreman to talk with the pump operator. Whenever you talk with an operator about the condition of a pump, there are several things you should find out. First, when did the problem begin? If it occurred suddenly, the problem could be a complete failure of a part. If the problem developed over a period of weeks or months, it's more likely to be the result of wear. Second, find out about any changes in pump status. Has the discharge pressure or suction pressure changed? Are there any unusual noises or signs of abnormal leakage? And third, check on what action the operator took to find out the cause of the problem. Were the strainers checked? Are the suction and discharge valves open all the way? Remember, anything the operator can tell you about the condition of the pump is to your advantage. When the operator or maintenance foreman has filled you in and the unit has been tagged out, you're ready to make your own inspection of the pump. Look for clues that might tell you what the problem is. Since this pump is running, the mechanic starts by checking for symptoms he can hear, feel, or see. He listens for unusual rattling or clanging noises that could mean a broken part or a foreign object loose inside the casing. Then he feels the casing itself for signs of excessive vibration. He also checks the bearing housings for vibration, and at the same time, he makes sure that the bearing temperature is normal. Excessive temperature and vibration of the bearing housings are almost sure signs of bearing problems. If you detect an unusual noise, use a sounding rod or a stethoscope like you see here to pinpoint the source of the sound. Growling or high-pitched howling or screeching sounds in the bearing are a common indication of bearing wear or damage. Notice that he checks the casing also to locate any abnormal noises coming from inside the pump. Using a stethoscope or a sounding rod is a good troubleshooting technique, but be careful. Loose clothing and objects that fall out of your pockets can get caught in the machinery. You could get pulled in yourself, and pencils turn into dangerous missiles when they bounce off rotating parts. Among the unusual noises that indicate problems, there is one that can't be mistaken for anything else. This is the sound of cavitation. When we look inside the pump, we'll see what causes it and what effect it has on the pump itself. For now, the one thing you have to remember is that if you hear this sound, you should immediately suspect cavitation. Once you've checked for unusual noises, the next step is to locate any excessive vibration. There are vibration metering devices that you can use for this purpose. One important thing to remember when using a vibration instrument is to carefully check the instrument before taking any measurements. Checking the condition of the device ensures accurate readings. Beginning with the bearing housings, take vibration readings by touching the probe to the surface of the pump. The bearings are checked first because excessive vibration often starts here as a symptom of bearing wear or damage. Next, take readings at other points along the surface of the casing to detect unusual vibrations inside the pump. Accurate vibration measurements give you important information that can lead to a proper diagnosis of the problem. Another device that can make your troubleshooting job easier is the temperature measuring device you see here. This instrument is called a pyrometer, and in troubleshooting, it gives you accurate readings of the temperatures of the bearings and the stuffing box. When using a pyrometer, Be certain the heat-sensitive cup at the tip of the probe is held firmly against the surface of the pump. And be sure the indicator on the dial has stopped moving before going on to test another spot. If you detect unusually high temperatures in either the bearings or the stuffing box, make a note of it. These are important clues as to what the problem is. That pretty well covers unusual noises, vibrations, and temperatures that you might find. Now, what about symptoms you can see? One of the best indicators of problems inside the pump is the reading on the discharge pressure gauge. If the reading is abnormally low, you can be sure that something has gone wrong, either with the pump or the gauge itself. The gauge should be checked by the instrument shop. If it's okay, a gradual drop in discharge pressure usually means excessive wear of one or more of the parts. A sudden drop, on the other hand, could indicate any of several things. It's possible that either the suction valve or the discharge valve is closed or partially closed. To check for this, trace the pump piping back to where the valves are located. Then check each valve to be sure it's in proper operating position. A sudden drop in discharge pressure could also result from air leaking into the pump casing. Air leakage causes the pump to lose its priming. One method of testing for air leaks is by moving an open flame along the pipe flanges and around the surface of the stuffing box. Air leaks in these areas will cause a noticeable distortion of the flame. One word of warning, however. Open flame tests should never be used in areas where open flame is prohibited or on pumps that move combustible materials. In cases where open flame tests can't be used, use one of the other testing methods described in your text. Another cause of low discharge pressure is an impeller that's mounted backwards on the shaft. In most any pump you work with, the impeller vanes must curve opposite the direction of rotation. If they curve the other way, they won't be able to move the water as well as they should. So, when replacing an impeller, be sure to mount it so that the vanes curve away from the direction of rotation. Finally, sudden decreases in pressure can be caused by damage to pump parts. A foreign object entering through the suction eye could seriously damage the impeller vanes. It could also block the suction. Foreign objects and fragments of broken parts should be removed as soon as possible. The longer they're inside the pump, the more damage they can cause. Work accidents are another cause of pump damage. Let's face it, in the course of repairing equipment, accidents do happen. If you accidentally damage a part while working on it, replace it if you can, or report the damage to your supervisor. Don't ever leave a broken part in a piece of equipment. We all make mistakes, and it's better to admit accidentally damaging something than to hide it and run the risk of seriously damaging the entire system. Okay, so much for accidents. Now, what else can you check for with the pump running? Well, one obvious thing is the amount of leak-off. Too little leak-off can mean that the gland follower is too tight, or that the gland sealing line is blocked or closed, and the gland isn't getting enough lubricating fluid. Too much leak-off is another common problem. It usually means that the packing is worn or the gland follower needs tightening. Once again, experience will teach you how much leak-off is the right amount for the pump you're inspecting. Another symptom you can check for is lubrication leaking from the bearing housing. Leaking grease can be an indication of serious problems. So if you see it, make every effort to determine where the leak is coming from and what damage, if any, has occurred. On some pumps, you'll find that lubricating oil is fed into the bearings by clear glass reservoirs like the one you see here. If the reservoir is empty, as this one obviously is, it's easy to refill it. Be certain you use clean lubricant of the type recommended in the manufacturer's instruction manual. Now, there is one trick to refilling oil reservoirs like this one. That is, flipping it over and setting it back into place without spilling oil all over the pump. This mechanic makes it look easy, but you'll probably find that it takes some practice to do the job as smoothly as this. We've tried to divide the symptoms into those you can hear, those you can see, and those you can feel. But most often, you'll find that problems cause more than one kind of symptom to appear. For example, worn bearings will not only be noisy, they'll probably be overheated too. And a damaged impeller can be indicated by a drop in discharge pressure, as well as by broken fragments rattling around inside the casing. Regardless of what symptoms you find, they are only symptoms. To get to the root of the problem, you'll probably have to open the pump and inspect the parts. If the problem is cavitation, which we heard before is a loud rattling noise, what you'll probably find is an impeller that looks like its edges have been sandblasted. The pump this comes from moves only clean water. There is no sand or other particles in the fluid. So what causes this kind of erosion? Collapsing bubbles. That's what cavitation is. Damage caused by tiny bubbles collapsing along the edge of the impeller. To see where these bubbles come from and what causes them to collapse with so much force, we have to start at the suction eye. Remember that pressure at the suction eye is lower than anywhere else in the pump. It has to be to create enough suction to draw water in. Also, keep in mind that there's a direct relationship between pressure and the boiling point of fluids. As the pressure increases, the boiling point increases. As the pressure decreases, the boiling point also decreases. This means that if the pump is moving hot fluids, these fluids have more of a chance of boiling at the suction eye, where the pressure is low, than in any other part of the pump. When boiling does occur, bubbles form in the fluid. These bubbles move with the fluid out toward the edge of the impeller, where the pressure is greater than it is in the suction eye. Under increased pressure, the bubbles collapse so quickly that they create powerful shock waves. These shock waves act like tiny jackhammers and can easily chip the outside edge of the impeller. Cavitation can be eliminated by having enough pressure at the suction of the pump to prevent boiling, or to use the proper term, enough available net positive suction head. Available net positive suction head, or available NPSH, is designed into the pump for a specific range of temperatures. The higher the temperature of the fluid being pumped, the higher the available NPSH has to be to prevent boiling and cavitation. As long as a pump handles fluids within the limits of its available NPSH, there's no problem. Problems will occur, though, if the operator forgets to open the suction valve all the way, or if the suction valve is blocked somehow. Any decrease in suction will lower the pressure, allowing cavitation to take place. So, if the pump shows signs of cavitation, ask the operator to check the position of the suction valve. A partially closed valve could be the problem. Cavitation could also result from running the pump too long with the discharge valve shut. When this happens, the water has nowhere to go, and friction between the spinning impeller and the water generates heat inside the pump. If this temperature gets high enough, the fluid will boil and cavitation will occur. To prevent this, most centrifugal pumps have a recirculation line that circulates water from the discharge back into the suction when the discharge valve is closed. Besides cavitation, another common problem to look for is worn or damaged casing wearing rings. These rings separate the suction from the discharge. If they're damaged, discharge fluid can leak back into the suction, lowering the discharge pressure and overall efficiency of the pump. Because of this, worn casing wearing rings should always be replaced. Well, that pretty well covers the basics of troubleshooting a centrifugal pump. Now, let's see how well you can apply what you've learned. Earlier today, a pump operator submitted a work request for a pump that's developed some definite problems. The maintenance foreman received the request, and now he's on the way to investigate the situation. Let's listen to the way the foreman finds out the details he needs to start the repair work.
Norris, did you submit that work request on number 2 river water pump?
Yeah, that's the one I wrote up and turned in this morning.
Well, I'm down here to investigate. You think we can go over and take a look at it?
Yeah, no problem at all.
Well, what's she doing this time?
Well, over the past week, she's steadily been losing discharge pressure.
How's your strainer differential?
We changed over strainers this morning, and it had no effect on it at all.
Any unusual noises out of it?
Off and on, but nothing I was really worried about.
Have you checked your flow rate upstairs?
Yeah, we had lost some flow.
Loss of flow? Loss of discharge pressure? Well, I think I know what's the matter with it this time. We're going to have to go into it. You think you can make arrangements to get it tagged out for us?
Yeah, no problem there.
Okay, if you could, I'd like you to do it first thing in the morning because we're going to be pretty busy.
Okay, I'll go ahead and get it tagged out now.
Okay, sure appreciate it.
Okay, we'll see you then.
Obviously, the foreman found out enough to determine what the problem is. From what the pump operator said, can you diagnose what's wrong with the pump? Well, we heard the operator say that he's noticed a gradual drop in discharge pressure. He did not mention any excessive noise, vibration, or temperatures, though. And he had checked the strainers to make sure they weren't the problem. Assuming that the suction and discharge valves are open all the way, what would you guess the problem is? Well, you can discuss your answer with your class and your instructor. Then, in the next unit, we'll overhaul this centrifugal pump. Since the same problems exist in this pump that the operator reported in the other one, we'll find the answer when we disassemble this pump and inspect the parts. But remember, finding the damaged part or parts is only half the solution. You have to find the cause of the damage too. If not, the damage will simply keep occurring over and over again to every replacement part you install. You can stop the tape now and review the material we've covered in this segment.